So which one? So 18 is four different problems, right?
Yeah.
So is there one?
G and H.
G or H? So we're looking for consensus among the class of difficulty. Last chance for a nomination?
18B.
Yeah.
Or B? Last chance. Any others?
Do you have a specific, pick a specific one for 2 and 8 to 2?
No, because no, those are just multi-questions, but 18 is four different problems. Are we good? So we can do 2 and 8, and then we'll just, when we get to 18, we'll see which ones we want to talk about. G, B, G, and H. Okay. So 2. The idea with 2 is the ratio of T, amount of T, to the amount of water, or no, corn syrup. So the amount of T is always 1500. And the amount of corn syrup changes. Okay, it's so we're putting different amounts of corn syrup in, and so that ends up being our input variable. So that function, which outputs the ratio of T to corn syrup, is the rule is 1500 over X. We good so far? So if you put in 1, this is saying if X is the input of 1, then you're saying that you're going to put in 1 gallon of corn syrup. And what will the ratio be? So the ratio is really talking about what's the relative amount of T compared to the amount of corn syrup. All right. So if there's 1,500 gallons of T and 1 gallon of corn syrup, then the relative amount of T to corn syrup is 1,500. But if you put in 1/10 of a gallon of corn syrup, now what's the relative size? How much T do you have relative to how much corn syrup you have? If there's only, yeah, so now there's 10, the relative size is 10 times as great. Because the 1,500 to 1/10 of a gallon means that there's 15,000 times more T than corn syrup. That's what the ratio tells you. How many more times there is of T than there is corn syrup. So as you keep putting 1/10 of what you had before, you're always going to get 10 times the ratio. So if you put in 1/1000th of a gallon, which is just a couple drops, or just a little bit, then you have 1,000,000 times as much T as you do corn syrup. That's what that ratio tells you. The relative amount of T to corn syrup. So we look at the numbers here. And this is X approaching 0 from the right or from the left? Positive values getting smaller would be approaching from the right, and we say X approaches 0 from the right. That's what they're saying down here. And what happens to that ratio? As X approaches 0 from the right, f of X increases. How big? As big as you want. You just put less and less corn syrup in, and you can make that ratio as big as you want by putting less corn syrup in, because the ratio is the relative amount. Okay, so I didn't go through A, B, C, D, but I just talked about it. I probably hit on all the main ideas. Does that clear up number 2? Any questions on number 2? Does it help? Okay, what was next? Number 8? So this is just talking about the behavior. So -1. What's important about -1 in this function? What kind of asymptote? That's a vertical asymptote, right? Because it's making a 0 in the denominator. And so we said at -1, if you have a 0 in the denominator, you get an asymptote. So this is saying approach -1 from, can you see that? Yeah, from the left. So this first question is, as x gets closer from the left, really what we're saying is, there's two possibilities. Either the function will head down to -infinity or head up to positive. So all you have to do is pick a number close and see if you get negative or positive. And then you can make that determination. So if you picked, so what would be a number coming from the left of -1? -2. But just to be sure, let's go a little closer than that. Well, we want to be close to -1. So how about -1.1? That's probably sufficiently close. So if we put -1 point, we don't have to find the value. All we have to do is enough to see if that's going to be negative or positive, and that'll tell us, are we heading down to -infinity or up to positive? So -1.1 will make the numerator negative or positive? Negative. -1.1 plus 1, negative or positive? Negative. -1.1 minus 3. Still, all of them are negative in this case. Therefore, at -1.1, what is g of x? Negative. So as x approaches -1 from the left, g approaches or gets infinitely large negative. We just tried a number close over here, just to the left, -1.1, and saw that all three of these are negative, and that will make a negative. Yeah.
Is it okay if we kind of do like number 2, where you plotted 3 numbers and saw a trend, and then saw if it was like getting more negative or more positive?
So you just did more than one number.
Yeah.
Yeah. Yeah. So, but really, if we're close enough, all we have to do is just see close enough to -1. Do you get a negative or a positive, and then that'll. Yeah, because there's no root. There's no root here to the left that it could cross back through. You see? So once you get close enough and you find that it's negative, it's not going to cross back through and do the other. So it's got to be negative. But yeah, doing more than one of numbers is fine. Yeah, totally fine. Okay, coming from the left, well, now we can use the logic we used last time in class. What's the multiplicity on that asymptote? Multiplicity of 1, right? The power is 1. And what did we say about multiplicity 1 on a vertical asymptote? Opposite or same side? Yeah, change the sign, or opposite. So if this from the left, if it's getting very large negative, then from the right, if the multiplicity is 1, it's going to be very large positive. So as x approaches -1 from the left, we're going to get very large negative numbers, and as x approaches -1 from the right, we get very large positive. Or you could put in, what's the number close to -1 to the right? 0.9? -0.9 is a number to the right, so you could plug this in, and your result ought to be positive. You ought to get a positive result if you use the same reasoning we did here. Does it clear up number 8? Any further questions on number 8? Okay, so 18. No, they've been turning them on the side. I don't have them. Okay, so was it B, G, and H? So here's B, x over 2x plus 6. G is this one, x minus 11 over x squared minus 5x plus 6. And then H is x times x plus 2 over 4x plus 1. So let's take a quick vote. All in favor of seeing B? All in favor of seeing G? All in favor of seeing H? All right, we'll do G and H. Okay, so so we're going to go through we're going to go through all 4 steps. So let me just put it in first. So our function is x minus 11 x squared minus 5x plus 6. Okay, so we want to go through the whole analysis. Let's see what we come up with here. Let's zoom out one time. Okay, so what's the first thing we want to look at? Roots. Okay, so what are the roots of the whole function? The roots of a rational function you look at? Whatever makes the numerator 0 will make the whole fraction 0, and therefore the function 0. So we look at, for the roots, we look at the numerator. So do we have any roots? So we got a point, 11. Okay, vertical intercept. What's true about the vertical intercept? Vertical intercept is what's always true along the y-axis. The output is 0. Is that right? Input is 0. X is 0. Is that right? So the input is 0. Good. Okay. And so then what output do we get? Which is almost negative 2. Negative 12.6 would be negative 2, so we're just shy of negative 2. So we got those 2 points on our graph. Next, third thing we look at. Vertical asymptotes. Okay, to get that, we need to factor the denominator, which is x minus 3, x minus 2, which gives us vertical asymptotes at 2 and 3. So I'll sketch the graph in red. Ignore this. Okay, oh, last thing, end behavior. End behavior will be, so we look at this, the end behavior will be, we'll look at the leading term in the numerator and the leading term in the denominator. Gives us x over, which is basically, so what are we saying? As x gets very, very large, positive or negative, this whole thing will behave just like 1 over x. It'll get closer and closer to 1 over x. So let's get a little sketch. So as x gets very, very large, positive, what does 1 over x do? Yep, gets closer and closer to 0. And as x gets very, very large, negative, what will that do? Still get close to 0, but now from negative values, right? From negative values. No, so you look at, so the right end is x going to positive infinity. That's way out to the right. So as x gets very, very large, what happens to that ratio? Take 1 over a million, 1 over a billion, 1 over a trillion. You get closer and closer to 0. So y gets closer and closer to 0, but from the positive side. Then as x gets very, very large, negative, we still get closer and closer to 0. It's just that we're doing it from the negative side. So all those very small fractions will be negative. So there's our end behavior. So let's do that. I'll do the graph one. So the end behavior says that as we get way out to the right, it'll get close to 0, and as we get way out to the left, likewise, it'll get close to 0, but from the negative side. There's our end behavior. So coming from right to left, we got to hit this root. Now we're going to get closer and closer to this asymptote. Will it go up to positive infinity or down to negative? Down, because this multiplicity is 1, so it has to cross, but it can't cross again because there's no more roots. So it's going to cross through and then go down to negative infinity like that. Okay, what are the multiplicities on these? 1, so that means opposite infinities or same side? Same infinities. opposite. We almost had it on every single one. So then if it goes down to negative infinity on the right side, it goes up to positive on the left. Okay, coming this way. It's going to go through our y-intercept, again, down to negative, or through the x-axis and up to positive. No roots here. Therefore, down. And then, multiplicity 1, opposite infinity. So on the right side of this, it's also going to go up to positive. Now, so this has got to come together and join together. There's got to be some low point, but that low point has to be above the x-axis because there's no roots in there. It can't cross. So our final graph looks something like this. So I'll graph it in purple and we'll see if we got it all. So we got the right idea there. That's good. This, I'm going to have to zoom out more. It's actually, this minimum is up higher. It's off the graph, so I'll zoom out. This looks good. So what you can't see is it's actually coming through there, and then it's up above, just like we said, and then over time it'll approach 0. So we had the right idea there. So just zooming out on the y-axis, we'll see that dip. There it is. See it? So now you just got to zoom out far enough, and we got that right behavior there. Questions on this one? Okay, so for time's sake, we don't have time for H. This one got more votes anyway. So if you want to go over H, you can do it after class or office hours. Happy to work on that with you another time. Any more questions about this example? Okay, so what we'll do is we'll start Module 7, Worksheet 1 together. We're going to work on that together. And then I'll put you to work on an activity. During the activity, I'll give out the rest of the exam slips. And at the end of class, we'll go over the most commonly missed items on the exam. So go ahead and open up to page 267. Okay, so the rest of the semester we'll be doing Module 7, which is trigonometry. Some of you have had some trigonometry before. I just want to warn you that the way that this text treats it is really different. It's pretty innovative, pretty original. So with that in mind, if you're trying to anticipate, if you're always reaching back to what you learned before and you're trying to anticipate, that might become confusing for you if I don't make it to the exact place that you remember, okay, in terms of the ideas and the problems. So it's probably going to be best if you just pretend we're starting over with angles and trigonometry, and don't, like I said, don't try to anticipate where I'm going, because you say, oh, I know this, I've done this before. Well, it might turn out to be different, and then you'll just be confused. So really try to stay with me and pretend this is all new, okay? So first thing we got to do is define what an angle is. So an angle consists of two rays with the same endpoint. So a ray it's like you start at a point and you go on in one direction, kind of like half of a line, okay? So if you take two rays and have them at the same endpoint, that will form what's called an angle. So one way to think about an angle is kind of like a door. So like this is the threshold of the door. One of the rays is kind of the boundary of the door, and then the other ray is like the door itself. And so the vertex then would be like a hinge. So the hinge, and we know that to get through a door, you open it on up, it turns on the hinge, and then that threshold remains in the same place. Okay, so at any given place where you stop the door, that would create an angle. Okay, that would create an angle. Two rays with a common endpoint. So the first question on your worksheet is, what does it mean for two angles to have the same measure? What does it mean for two angles to have the same measure? So why don't you talk with a partner, write out what you think, And this is just open-ended. Just write out honestly what you think and not, I got to get it right. Okay, so just write out what would it mean for two angles to have the same measure. Go. Take a minute to do that. Get a partner, talk about it. And we'll do one more set of these. Just like everyone else's sheets. Explain it. Just like everyone else's, okay? Let's do last names I through L. Just last names I through L. Come on down.
Jackson Small or Small Jackson.
Oh, sorry.
Thank you.
Last name? Dominic?
Crane, K-R-A-N.
Michael?
Yep. Thank you.
Garrett?
Yes. Thank you.
Audrey? See you later. Okay. What's the last name?
Johnstone. Thank you.
Okay, ideas. Well, actually, so I kind of set you up. So I wanted you to think about that, but really, there's a question we have to ask before we can answer this one. And so let's take a step back. Really, we have to know when we're measuring angle, what characteristic of the angle are we assigning a value to? So I've got this. This goes back to the idea of quantities, right? So we have this object, the angle. So maybe it's like this. Okay, there's our two rays, there's our vertex. So that's the object, the angle. So what attribute or characteristic of that are we measuring when we assign a number to it? When we measure the angle and we assign a number, what is the attribute or characteristic of the angle that we're quantifying? Yeah. The openness. Yeah. The vertex? Not quite. Yeah, when you're measuring the angle. So if it only were the vertex, then
You want like the degrees apart?
no. So you're way too far ahead. So if it were just the vertex, then these two would have the same measure. Do you see? It's got to be something to do with the rays. Any other ideas? What's that? How far apart? Okay, so that's a good idea, but there's kind of a problem with it. So looking at this blue angle over here, why does how far the rays are apart not really work? Yeah, as you get further from the vertex, what happens to the distance apart? Increases, right? So how far apart are these? Well, it depends on how far you are away from the vertex, you see. Any other ideas?
Distance apart, like looking at a circle. You have a circle, right?
Okay.
And the vertex is the center point.
Okay.
The distance between them.
Something to do with a circle. Put the vertex on a circle and kind of look at maybe arc length. Okay? Other ideas? Okay, so those are all good ideas. So one person nailed it. It's the openness of the rays. So if you think about the door, if the door is closed completely, what number is that for openness? 0. That's a 0 angle. So then as we open the door more and more, the value, the measure of the angle will increase. So how open it is that will be what we're quantifying or what we're assigning a number to. Okay? So just, we're not actually putting the number on yet, but just order these angles from least to greatest openness. Go. Talk with your partner. Least to greatest openness. Okay, what's the least? C is the least open. So when we put a number on it, it'll be the lowest value. Okay? And then next greatest, A is next largest, and then the final, the largest amount of openness is B. So when we assign a number, this will be the lowest number, and this will be the highest number. Okay? So the openness corresponds to the value that we assign, we measure. Okay, so now we want to talk about actually assigning a value. And so how do we do that? How do we actually assign a value to the openness of an angle? In other words, in general, what's the basis for measuring angles? Okay. All right, so some people are saying so degrees or 360. So we're even stepping back before that. So how do we get those numbers? So what do the numbers mean? What's the basis for measuring an angle? So in order to help you kind of discover the answer to this, there's a little activity, and this is actually like number 2. And it's to design the blueprints for a pizza cutter. Okay? So if you were to design, so here's 2 different styles, but it's really the same question in both cases. We want to, how would you design a V-shaped pizza cutter? So like, here's the V here, or here's the V here. How would you design it so that you cut the pizza into exactly 9 equally sized wedges? So you want exactly 9 from your circular pizza, okay? So here's the ground rules though. You don't have a protractor, and you can't use any circle formulas. So no cranking out formulas. But to make this blueprints for your pizza cutter, these are the things you have. Common desk supplies. Pencil, ruler, tape, scissors, string, etc. So how can you use just these things to make a blueprint to design a pizza cutter that would get exactly 9 equally sized wedges? Is the task clear? All right, in number 2, it talks about 11-inch diameter. You can ignore that. Doesn't ignore the diameter. All right, any questions on what you're doing while I turn back the rest of the thing? So this is kind of like a okay, so idea to precisely design this thing, get a blueprint with just scissors, pencil, tape, whatever. So, anyone think they can do it exactly? Yeah?
Yeah, I'm discussing, you take your tape measure,
Okay.
and measure the outer edge all the way around.
You got a ruler and a string. You don't have a tape measure.
Against the ruler.
What's that?
Grab the string against the ruler. Yeah.
Okay, so what are you going to do?
And then find out how many inches all the way around. Divide that by 9.
Okay, so how are you going to get all the way around again? Start from the beginning.
Well, I was saying measure from one point and measure all the way around the whole pizza.
How are you going to do that?
Well, you have a ruler.
The ruler is straight.
But you can't move the ruler.
No, that wouldn't be accurate measurement at all. Yeah.
You'll start with the string, get a
Yeah, so
measurement
what you said was right. We gotta, yeah.
of the circumference of the pizza,
Put the string around the edge.
and then once you get back to your starting point, you're going to take the string, you're going to mark where it was at on the string, and you take the string, straighten it out, measure with the ruler,
Okay.
do 9 individually.
Okay, and then so take this is the perimeter or the circumference of the circle. You're saying divide it up into 9 equal pieces. So that would be like 1/9 of the circumference. Okay, what from there? Somebody else take over. Find the center point, okay.
And a line from those segments to the center.
So like this.
Well, put it back around the pizza,
Okay, so now we're going to put it back on the pizza.
and then cut it.
And I'll know where my 1/9 of the circumference is. And so we can design for this one, we can design this little tray here, this tray thingy. based on, so what is the whole thing based on then? No, what is the angle, that openness, how are we getting that, and just in general, how are we getting that openness? What's it based on? Yeah, it's based on the circumference and, yeah, it's like a ratio or a relative arc length, right? So it's based on arc length. Someone had said that earlier. So that's what that openness is based on. It's based on like the fraction of a full rotation, or the relative size of the arc compared to the whole size of the whole circumference. That can precisely get us what that amount of openness is using that fraction arc length of the whole circumference. So it's a really big idea. This is how we are going to form angles. So the measurement angle is based on, this is kind of two ways to think about it. Percent or fraction of a full rotation. What fraction did we do? We did 1/9, right? So that angle was based on 1/9 of all the way around. Okay? And we used the arc length. So we could say the circular arc length relative to the whole circle, the circumference of the circle that you're using. So no matter whether you use degrees or there's half a dozen ways that man has invented to put a number on angle, but all of them are based on this. Doesn't matter whether you use degrees or something else. Every single way that you can assign values to angles, measure an angle, they're all based on this. Percent or fraction of rotation or circular arc length relative to the circumference. Anybody have a question? So let's